Have you ever slammed your hand on a table maybe out of frustration, maybe just to prove a point and thought, ouch, that's solid? Well, here's the twist. That table you just smacked is made almost entirely of empty space. Yep, the wood, the grain, the polished surface, all basically nothing. If atoms are these tiny little voids with a speck in the middle, why can't your hand just fall right through? Like you're some budget version of Casper the Friendly Ghost. Why does the table fight back? This is the paradox at the heart of our existence. Everything solid around you is built out of things that aren't solid at all. That's wild. Let's unpack it together. So what is an atom, really? Let's zoom in on your hand. First you pass the skin, then the cells, then the molecules. Keep zooming and zooming until you're face to face with atoms. These little guys are so small that a single grain of sand contains more atoms than there are stars in the entire observable universe. Yeah, wrap your head around that next time you're at the beach. Each atom has a tiny but mighty centre called the nucleus. That's where protons and neutrons hang out like bouncers at the VIP section of a nightclub. Electrons. They're the restless partygoers zipping around the edges so fast you can't pin down where they are at any given moment. You'd think of them like planets around the sun, but reality is messier. They're more like a swarm of bees that drank too much espresso chaotic buzzing and everywhere at once. Here's a mind bender. If you scaled up an atom to the size of a football stadium, the nucleus would be a tiny pea sitting at the 50-yard line. The electrons would be buzzing way up near the nosebleed seats, and everything in between nothing, just empty air. So again, why can't your hand pass through? Which brings us to the next big question: do atoms ever touch? In your daily life, touching feels obvious. You touch your phone, you touch a keyboard, you pet your dog, but zoom into the atomic level and surprise, atoms never actually touch each other. Instead, what you feel is the invisible pushback from electromagnetic forces. The electrons in your hand repel the electrons in the table. That invisible repulsion is what your brain interprets as touch. Imagine two people trying to hug while wearing giant inflatable sumo suits. They never really get close, but the squishy resistance makes it feel like they did. That's how atoms touch. So when you're scrolling TikTok on your phone and your finger taps the screen, sorry to break it to you, you didn't really touch your phone. Your electrons just got really, really pushy with the electrons in the glass. And while we're asking strange questions, here's another one: are all atoms identical? If atoms are the Lego blocks of reality, does that mean every Lego piece is identical? Not exactly. Take copper atoms, for instance. One might have its electrons all calm and stable. Another might have an electron buzzing in an excited state like it just had too much Red Bull. Even though both are copper, they behave differently. Kind of like siblings, same family, very different personalities. And then you've got isotopes. These are atoms of the same element but with slightly different numbers of neutrons in the nucleus. Chemically, they'll act almost the same, but in nuclear reactions, totally different story. That's why carbon-12 makes up your body, while carbon-14 helps archaeologists figure out how long ago a mammoth had dinner. So no atoms aren't perfect clones. They're more like a family reunion, lots of shared traits, but also plenty of quirks, which naturally leads to yet another curiosity. Do atoms have colour? It's a fair question. If everything is made of atoms, do atoms themselves have a colour? The short answer: nope. Colour as we see it is a trick of light and our brains. When light hits an object, say your favourite blue hoodie, some wavelengths of light get absorbed, others get reflected. Your eyes catch the reflected part and boom, you see blue. But an individual atom, it's way too small for visible light to bounce off in a meaningful way. It'd be like trying to paint with a brush the size of Texas on a single grain of sand. You're just not going to get detail. That said, atoms can glow in their own quirky ways. Give them energy, and their electrons jump to higher energy levels. When they fall back down, they release light of very specific colours. That's why neon signs glow red-orange, why fireworks sparkle green and blue, and why sodium street lamps make everything look like a scene from a bad 70s cop show. Each element has its own colour signature like a cosmic barcode, but a single atom floating alone, invisible to your naked eye. If we zoom out from all this weirdness, what's the big picture? Atoms are mostly empty space. They never actually touch. They're not perfectly identical, and they don't have colour in the way you think, and yet pile enough of them together and you get oceans, buildings, dogs, guitars, French fries, and even you. Somehow stacking a bunch of mostly empty invisible particles gives us a solid, colourful world. That's not just science, it's practically magic. The mystery here isn't only about physics, it's also deeply philosophical. How can emptiness feel solid? How can invisible particles create sunsets, skyscrapers, and Spotify playlists? The answer lies in the strange rules of quantum mechanics. Rules that atoms follow like dancers in a cosmic choreography. But knowing what atoms are only raises the real question. Where did they come from? Atoms didn't just pop into existence fully formed like pre-assembled IKEA furniture. The universe had to build them from scratch. First, pure energy somehow morphed into particles. Then those particles grouped into protons and neutrons. Eventually they linked up with electrons. Only after an unimaginably chaotic cosmic party did the first atom settle down. So the next chapter asks, how did nothing literally a void before space and time turn into everything? How did raw energy transform into the first tiny building blocks that would someday become stars, planets, people, and your morning coffee? That's the mystery waiting in part 2. And trust me, it involves wild explosions, time measured in billionths of a billionth of a second, and the universe inflating faster than light itself. Sounds impossible, maybe. But it's the story that explains why you're here listening right now. So grab a seat because the ride's just getting started. Let's rewind for a second. We already know that atoms are mostly empty space, but here's a deeper question. Why don't they just fall apart? If you've got tiny electrons zooming around a nucleus, what keeps the whole system from collapsing like a badly built Jenga tower? Instead of jumping straight to the answer, let's start with the first big idea scientists had the solar system model that didn't work. Back in the early 1900s, scientists tried to picture atoms like a miniature solar system. The nucleus was the sun, and the electrons were planets orbiting around it. It was a neat idea, simple, elegant, except for one little problem: physics. See, whenever a charged particle like an electron moves in a circle, it should give off radiation. Kind of like a car burning gas while driving in circles. The electron would lose energy, spiral inward, and crash into the nucleus in less than a blink. Which means poof atoms should not exist. Not for 1 billion years, not for a second, just gone. But you and I are still here. The table is still here. Your cat is still staring at you. So clearly something in that model didn't add up. That's when a bold thinker entered the scene. Bohr crashes the party. Enter Niels Bohr, a Danish physicist with a knack for breaking the rules. In 1913 he proposed something radical. Electrons don't just orbit at random distances like planets. Instead, they're only allowed to sit in specific quantized orbits, like steps on a staircase. They can't stand between the steps no matter how much they want to. And here's the kicker. An electron can only jump from one orbit to another if it absorbs or releases exactly the right amount of energy. That's it. No discounts, no half measures. Imagine a vending machine that only takes exact change. You can't cheat it with a penny, more or less. This solved the mystery. Electrons weren't constantly losing energy because they weren't allowed to exist in in-between states. They were stable in their quantized orbits like bowling balls, magically balancing on certain shelves and nowhere else. But Bohr wasn't working alone in this revolution, because long before him came another big idea: Planck's tiny packets of light. Max Planck had introduced the idea that light and energy don't come in smooth, continuous waves. Instead, they arrive in discrete packets called quanta. Think of it like M&Ms. You can grab 1 or 2 or 3, but never 2.6 M&Ms. Nature works in whole number chunks. Bohr simply applied this thinking to electrons. The angular momentum of an electron, the measure of how it's spinning around, must be exact multiples of Planck's constant. No fractions allowed. And just like that, the model of the atom went from collapsing disaster to stable masterpiece. But wait, things get even stranger when you realise that electrons behave like waves. They aren't just tiny balls zipping around, they also act like waves. And waves have rules. Picture a guitar string. You pluck it and only certain vibrations are allowed, those that fit neatly between the ends of the string. Try to vibrate it in a weird in-between pattern and it just doesn't work. Electrons are the same. Around the nucleus, only certain standing waves can exist. These allowed waves become the electrons' orbitals. That's why electrons don't spiral into the nucleus, they're trapped by the wave patterns, locked into energy levels that fit like musical notes. It's as if the universe is playing a cosmic guitar and electrons are forced to hum in harmony. So here's the essence the atom survives, because electrons aren't free to wander wherever they like. They're locked into quantized orbits obeying strange but reliable rules, and that simple fact changes everything. So we've seen how Bohr and Planck changed the game, turning atoms from a collapsing disaster into something stable. But the deeper you look, the stranger it gets. Because when scientists try to pin down where electrons actually are, they hit a brick wall. That brings us to the next curiosity: can we really know where an electron is? The answer is no, not exactly. Electrons don't follow neat orbits like planets. Instead, they exist in what we call probability clouds. Imagine throwing 100 ping-pong balls into a room with fans blowing everywhere. After a while, you'll notice some corners of the room fill with balls more often than others. That's what electrons do. They have places they're likely to be, but never a precise track. So when we draw those tidy diagrams in textbooks with little circles around a nucleus, yeah, that's mostly a lie we tell kids to keep things simple. Reality is more like a buzzing cloud of possibility, which leads to a very natural thought: if electrons are so uncertain, how can atoms feel so solid? Here's the twist: stability doesn't come from knowing exactly where electrons are. It comes from the fact that they can't all pile into the same state. This is thanks to something called the Pauli exclusion principle. Think of it like a music festival. There's only so much room in the front row, and once it's filled, new people have to stand further back. No matter how much they want to squeeze in, physics says, sorry, this seat's taken. Electrons follow the same rule. Each orbital can only hold a limited number, and once those slots are filled, the rest get pushed outward. This simple restriction is why matter has structure, why atoms form shells, and why chemistry even exists. Without it, the entire universe would collapse into a giant blob. Not very fun for chemistry class. Now let's push the idea further. What happens when electrons jump between these shells? This is where things get flashy. When electrons absorb energy, they leap up to a higher shell, but they can't stay there forever. Eventually they fall back down, releasing light. This is why neon lights glow, why the northern lights shimmer, and why astronomers can tell what distant stars are made of just by studying their light. Think of it like karaoke night. An electron gets hyped up, jumps onto stage belts out a note of energy, and then comes back down to the crowd. Different atoms sing different notes and the universe listens. And here's another mystery to chew on if atoms are mostly empty. Why do things feel solid at all? We touched on this earlier, but it's worth repeating when your finger presses against a table. It's not atoms colliding like billiard balls. It's the quantum rules of electrons refusing to let two atoms occupy the same space. The pushback you feel is the raw stubbornness of nature saying this far no further. In other words, solidity is an illusion created by resistance at the quantum level, which is wild because that means every time you sit in a chair, you're really floating on an invisible cushion of electron repulsion. Think about that next time you plop down on the couch. But stability has another side to it. What about the nucleus? Why doesn't it blow apart inside that tiny core you've got? Protons each positively charged. According to basic logic, they should repel each other violently. And yet they don't. Why? Because of the strong nuclear force. This force is like duct tape on steroids. It's far stronger than the repulsion of protons, but it only works at extremely short distances. If protons drift too far, the force weakens. But when they're close, like inside a nucleus, it locks them together tight. So the nucleus is basically a high-stakes tug-of-war electromagnetic repulsion, trying to push protons apart and the strong force gluing them together. The fact that the strong force wins is the only reason atoms exist. Without it, there would be no elements, no stars, no life, nothing but scattered particles. So here's the conclusion for this part. The atom survives because of a fragile but perfect balance. Electrons are trapped in quantized shells, refusing to collapse. Protons are held together by the strong force refusing to explode apart. It's a cosmic standoff that somehow produces order out of chaos, and yet the balance is delicate. Add too many protons and the nucleus becomes unstable, leading to radioactive decay. Push electrons too far and they ionize, flying off. Atoms may seem eternal, but in reality they're like tightrope walkers, always balancing forces, never truly at rest. The key idea to remember is this: the solidity of your chair, the glow of neon lights, the warmth of the sun, all of it comes down to the strange, stubborn rules of quantum mechanics. And if that feels strange, just wait. The next question goes even deeper. How did protons, neutrons, and electrons appear in the first place? What cosmic recipe brought them into being before atoms were possible? That's the mystery waiting in part 3. And it takes us all the way back to the very first seconds of the universe. So far we've looked at how atoms stay stable once they exist. But here's a bigger mystery: where did those atoms even come from? If we rewind far enough, we hit a wall, a time when atoms didn't exist, where not even protons or neutrons existed, just raw energy. Alright, so let's ask the uncomfortable question out loud. How does energy become matter at all? To even attempt an answer, we have to go back to the very beginning, or as close as physics lets us peek. The universe, as far as we know, began in what we call the Big Bang. Not a bomb going off inside space, but space itself, expanding from an unimaginably hot, dense state. Think balloon, not shrapnel. The balloon is space, and everything inside gets stretched as it inflates. But immediately there's a snag. Those first instants are almost indescribable. The timescales are ridiculous. The earliest slice we can meaningfully talk about is the Planck time, around 10:43 seconds after go. That's a decimal point, 42 zeros and a 1. If 1 second were stretched across the observable universe, roughly 93 billion light years, the Planck time would still be microscopically tiny. At that instant, our best theories don't cooperate. General relativity, gravity, the very large, and quantum mechanics, the very small, refuse to share a table. To truly know what happened, we'd need quantum gravity, a theory we're still chasing. So physicists take a clever detour start just after that during cosmic inflation. From about 10 ryan 36 to 10 ryan 33 seconds, the universe swelled faster than light. That's not breaking Einstein. Nothing moved through space faster than light space itself stretched. Picture an ant on a balloon. The ant crawls slowly, but inflate the balloon fast enough, and 2 ants can separate faster than any crawling speed. Inflation did that, ballooning the universe from smaller than a proton to roughly grapefruit size in a blink, which begs another question: what powered such outrageous expansion? The leading suspect is an energy field dubbed the inflaton. Yes, the name sounds like a working title, and it sort of is. We don't know its exact nature. We do know that when inflation ended, the energy didn't vanish. It reheated the universe, dumping its energy into a torrent of particles and radiation. Think of cracking open a badly shaken soda can. Pressure has to go somewhere. In our case, the inflaton's energy decayed into the first zoo of particles. At last there were ingredients. Now zoom in on the next act, the newborn universe, blisteringly hot, crammed with particles. By 10 first 12 seconds, cooling allowed the fundamental forces to separate. Before then, electromagnetism and the weak force were fused into the electroweak force. As the temperature dropped, they split like siblings, finally taking separate rooms. That split set the table for mass. Thanks to the Higgs field particles that have been zipping around weightless, suddenly slogged through cosmic molasses and picked up mass. No mass, no atoms. No atoms, no stars. No stars, no us. But when did the first building blocks appear? Welcome to the quark epoch. From roughly 10^12 to 10^6 seconds, things were too hot for stable structures. The universe was a roiling soup of quarks, which will later make protons and neutrons and gluons the glue that binds quarks. Try to ladle out a proton then, and it falls apart instantly. As expansion continued, temperatures fell. Cooling is everything here. Lower the heat and quarks can finally lock together, the first protons and neutrons appear. Here's where the timeline turns jaw-dropping. By 1/1,000,000th of a second, the universe already had the basic bricks, protons and neutrons everywhere. But there's a deadly waltz. Every proton pairs with an antiproton, every electron with a positron. Collide, annihilate, flash energy. So why is anything left? Because of a microscopic bias for roughly every billion matter-antimatter pairs, there was one extra matter particle. That 1 in a billion surplus built every star, every planet, every pizza, and you. Now for the honest part, why the imbalance, we don't know. It's called baryon asymmetry, one of cosmology's most stubborn riddles. Maybe it snuck in via subtle rule-breaking in particle physics. Maybe chance got a vote. Whatever the mechanism, we owe our existence to that tiny tilt. But we're not done. Protons and neutrons are flour and sugar. You still need eggs. To get atoms, electrons must join and nuclei must actually assemble. That messy, glorious chemistry starter is where we're headed next. When we last left the cosmos, it was stocked with protons and neutrons and blessed with that precious matter surplus. But protons plus neutrons, atoms. We need nuclei and we need electrons to stick. So how did protons and neutrons fuse into the first nuclei? Enter Big Bang nucleosynthesis, the universe's first chemistry set, beginning a few minutes after the start when temperatures cooled to 1,000,000,000 Kelvin. Compared to the trillion-degree furnace earlier, this was practically sweater weather. At these cooler conditions, protons and neutrons finally held together long enough to fuse into light nuclei, mostly hydrogen, a lone proton and helium, 2 protons, plus 2 neutrons with a dash of lithium for spice. Final mix. Roughly 75% hydrogen, 25% helium trace lithium. That ratio has held for 13.8 billion years. The stars you see tonight are still burning that primordial hydrogen. You might ask, why not heavier elements right away, carbon, oxygen, iron? Because the universe cooled too quickly. Heavy nuclei need slower cooking and higher stability. The early oven shut off before the cake could rise. Heavier elements would have to wait for the first stars to ignite and run their fusion factories. Next puzzle. When did electrons finally join the party? For hundreds of thousands of years, the universe was too hot for a stable atom. Every time an electron tried to settle around a nucleus, an energetic photon body checked it back out. Picture trying to sit at a concert while the mosh pit keeps tossing you no chance to rest. During this era, the cosmos was a glowing, opaque plasma-free electrons and bare nuclei with light ricocheting constantly. Photons couldn't get far without slamming into electrons. Think inside of a star, not clear night sky. The turning point came 380,000 years after the beginning recombination. By then, the temperature had dropped to 3000 K, roughly old-school light bulb filament hot. Electrons could finally sit in orbits without getting evicted. Neutral atoms, mostly hydrogen and helium, took shape. And when electrons settled, light was freed. The fog lifted. The universe became transparent. Those liberated photons are still flying. They're the cosmic microwave background CMB stretched by expansion, from visible light into microwaves. Why should we care about this faint afterglow? Because it's the universe's baby picture. Minute ripples in the CMB map tell us the age-shaped contents and future of the cosmos. Each tiny temperature wrinkle records where matter was slightly denser, seeds that gravity would later grow into galaxies. Next time you reheat dinner, remember microwave links, at least in spirit, to that oldest light. The afterglow of creation is everywhere. Our eyes just can't see in microwaves. So what did the universe look like once atoms finally existed? Imagine a vast starless ocean of hydrogen and helium, the cosmic dark ages, quiet but pregnant with possibility. Under gravity's pull, clouds of gas would condense ignite fusion and spark the first stars. Those stars would forge the heavier elements, carbon, oxygen, iron, that biology later borrowed to build life. Here's the sobering kicker: miss any of those early beats, and nothing follows. If quarks never congealed, if matter and antimatter perfectly cancelled, if cooling ran too fast or too slow, no galaxies, no chemistry, no people. Our existence is a relay race of fragile handoffs that somehow didn't drop the baton. We've reached a turning point in our story. In part 3, we left the universe at about 380,000 years old, dark, cooling, and finally calm enough for electrons to settle down with protons. That's when the first true atoms appeared. But what exactly happened in that cosmic moment? And why is it such a big deal? Let's start with the obvious. What does it mean to say atoms finally formed? Before recombination, the universe was a wild plasma nuclei flying around without electrons, photons bouncing endlessly like kids in a bouncy castle. Light couldn't travel freely, which means the universe was foggy, opaque, and chaotic. But as soon as the temperature dropped to around 3000 Kelvin, electrons were no longer blasted loose by every photon they met. Instead, they could finally sit down in stable orbits around nuclei. That's what we mean when we say atoms formed for the first time. The basic building blocks of matter actually held together. And here's the poetic part: when electrons paired up with nuclei, photons were suddenly free to travel. The fog lifted and the cosmos went transparent. It was literally the first dawn. Which brings us to a fascinating clue: the cosmic microwave background. That glow you sometimes hear astronomers talk about, it's the fossil light from this exact moment. Those photons released at recombination are still zipping through space today. Over billions of years, the expansion of the universe stretched their wavelengths from visible light into the microwave range. If you've ever seen snow on an old TV screen, a tiny fraction of that static was caused by the cosmic microwave background. Think about that. Every time people fiddled with the antenna in the 80s and complained about bad reception, they were accidentally seeing the afterglow of creation itself. But let's not get ahead of ourselves. What kind of atoms actually formed back then? Mostly hydrogen. Roughly 3 out of every 4 atoms were simple single-proton hydrogen. The rest were almost entirely helium with a sprinkle of lithium. That was it. No oxygen, no carbon, no iron. Just the simplest ingredients, hydrogen and helium floating through space. This may sound boring, but it was revolutionary. For the first time, the universe had matter that could clump together, feel the pull of gravity, and eventually form stars and galaxies. Without this stage, there'd be nothing but endless radiation. Now here's the next curiosity: if the universe was full of hydrogen and helium, how did it stay dark for so long? That era is known as the Cosmic Dark Ages. Even though atoms existed, there were no stars yet to shine. Imagine an ocean of invisible gas stretching in every direction, silent and lightless. The universe had cleared its fog, but it hadn't switched on any lights. It would take hundreds of millions of years before gravity pulled enough atoms together to ignite the first stars. Only then would the cosmos blaze with new light. Until that moment, the universe was a vast, quiet waiting room. But this sets up a deeper question. Why did atoms matter so much for the future of the universe? Because atoms provided stability. Once electrons locked onto nuclei, the universe had particles that didn't instantly fly apart. This allowed matter to clump together under gravity. Hydrogen and helium clouds collapsed, fusion ignited, and stars were born. And stars are cosmic factories churning out heavier elements like carbon, oxygen, and iron. Think of hydrogen as Lego bricks. Alone, they don't look like much. But stack them together in the right way and you can build castles, cars, or starships. Atoms are nature's Lego pieces, and recombination was the moment those pieces were first moulded. Now let's add some perspective. What would have happened if recombination had gone differently? If the universe had cooled faster, electrons might never have paired up with nuclei. If it cooled slower, photons might have stayed trapped much longer. Either way, the timing had to be just right. Too much variation and stars and galaxies may never have formed. In other words, the existence of atoms wasn't guaranteed. It was balanced on a cosmic knife's edge. The fact that electrons chose to settle down when they did is the reason you're breathing today. And here's something mind-bending: atoms didn't just create structure, they also gave the universe colour. Before recombination, there was no way for light to travel freely, which means no meaningful colours, no visible universe. Once atoms appeared, photons could roam carrying information. Suddenly there was a cosmic palette to paint with. If you could have watched the universe at that time, you would have seen a red-orange glow filling all of space, gradually fading as the cosmos expanded. That glow is still here, but stretched into microwaves invisible to our eyes. Next, they collide, bounce, and sometimes stick, launching the first chemistry. Let's see how that works. In the last chapter, we watched the fog of the universe lift as electrons finally settled down into orbits around nuclei. Hydrogen and helium were born, photons were released, and the cosmos went transparent for the first time. But atoms alone aren't the end of the story, they're just the beginning. Because once you have atoms, the real fun begins, they start to interact. So here's the next curiosity. What happens when atoms meet each other in the wild? On their own, atoms are like single people at a party, interesting, but not that exciting. The real drama starts when they bump into each other and form bonds. That's chemistry, atoms connecting, combining and building structures far more complex than themselves. At first, these interactions were simple. Hydrogen atoms occasionally formed pairs, becoming H2 molecules. Helium, on the other hand, was aloof. It's a noble gas, too stable to mingle much. But once stars ignited, the chemistry show exploded. Fusion inside stars forged new elements, carbon, oxygen, nitrogen, and suddenly atoms had many more ways to connect. But let's back up. Why do atoms even form bonds? The answer comes down to energy. Atoms prefer to be in lower energy states, just like you prefer lying on the couch instead of running a marathon. By sharing or transferring electrons, atoms can reach more stable configurations. Think of it like roommates splitting rent. Alone, it's expensive and unstable. Together, they share the load and everyone's better off. That's what happens when two hydrogen atoms share their electrons. They form a bond, lower their energy, and create a stable H2 molecule. This raises another question. Are all atoms equally eager to bond? Not at all. Some are clingy, desperate to grab electrons, while others are happy to give them away. Oxygen, for example, loves to steal electrons like that friend who always borrows your phone charger and never gives it back. Sodium, meanwhile, is generous to a fault, handing over electrons at the first chance. Put them together and bam, you've got table salt. It's this mix of personalities, electron donors, electron hoarders and electron sharers, that drives the incredible diversity of chemistry. Without it, the universe would just be a bland soup of hydrogen gas. Now here's a twist. Atoms not only bond, they also create properties that don't exist individually. Take water. A hydrogen atom on its own is a flammable gas. Oxygen on its own fuels fire. But combine two hydrogens with one oxygen, and you get water, the stuff that puts fires out. That's the magic of molecules. The whole becomes greater than the sum of its parts. This principle is why we have everything from diamonds to DNA. Carbon atoms alone are just tiny points of matter. Link them up in the right patterns, and you get the rigid lattice of a diamond, or the complex spirals of genetic code. But let's bring it back to the early universe. When did the first molecules appear? Surprisingly, even before stars formed, some molecules managed to exist. Simple hydrogen molecules. H2 were among the first, and they played a key role in cooling gas clouds so gravity could collapse them into stars. Without those early molecular air conditioners, the first stars might have taken much longer to ignite. Later, inside stars and exploding supernovae, more complex elements and molecules were born. These new atoms spilled into space, enriching future generations of stars and planets. By the time Earth formed, the periodic table was well stocked, and chemistry was in full swing. Now here's the kicker. The laws of bonding set the stage for life itself. Carbon is especially important. It can form 4 bonds at once, making it the ultimate social butterfly of the atomic world. This flexibility allows it to build endless chains, rings and frameworks perfect for complex molecules like proteins and DNA. Without carbon's unique bonding ability, life as we know it would be impossible. So when you look at yourself in the mirror, you're seeing the result of atoms that spent billions of years learning to cooperate. From lonely hydrogen nuclei in the early universe to complex carbon-based life on Earth, it's all one continuous story of atoms figuring out how to bond. But before we get too sentimental, let's ask one more cheeky question. Why don't atoms just merge into one giant blob instead of forming neat molecules? The answer lies in balance. Electrons repel each other. Protons attract electrons, and quantum rules limit where particles can sit. These forces create structure, preventing everything from collapsing into mush. In fact, it's this constant tug of war that gives matter its shape, texture, and resilience. Every time you touch a wooden desk, drink a glass of water, or scroll on your phone, you're feeling the result of atoms balancing attraction and repulsion in perfectly orchestrated ways. So let's tackle the first big question. If atoms are mostly empty space, why do things feel solid? On the surface, your desk feels firm, your coffee mug feels sturdy, and your chair is holding you up just fine. But zoom in and you'll see nothing but emptiness. A nucleus the size of a pea in a football stadium with electrons buzzing around like caffeinated bees. So why doesn't your hand pass straight through the desk? The answer is forces. Specifically, the electromagnetic force. The electrons in your hand and the electrons in the desk repel each other, refusing to overlap. The result is that invisible pushback you interpret as solid. It's a bit like trying to push two magnets together when their poles are aligned. You can't make them touch no matter how hard you press. That resistance is exactly what's happening at the atomic level every time you sit, stand, or hold anything. But here's a follow-up curiosity: if atoms never truly touch, are we ever really touching anything? The unsettling answer is not in the way we think. What we call touch is actually the sensation of electromagnetic repulsion. Your fingertips don't physically collide with the atoms of your phone screen. Instead, the electrons in your skin get close enough to the electrons in the glass to create a strong pushback. Your brain translates that resistance as touch. So technically, you've never touched anything in your life. You've only gotten very, very close. Comforting, right? Now let's push the weirdness further. If matter is mostly empty, why can't light pass through everything? If there's so much space inside atoms, shouldn't light just slip right through? But it doesn't. Wood, metal, stone, most things block light. Here's why electrons don't just repel, they also absorb and re-emit light. When a photon hits an electron, the electron can jump to a higher energy state. It might drop back down, releasing light again, but not necessarily in the same direction. Multiply that by trillions of atoms and the incoming light gets scattered, absorbed, or bounced around until it can't pass through. That's why glass, where the atoms are arranged just right, lets visible light slip through while blocking other wavelengths. And it's why your wooden desk is opaque. It scatters photons like a disco ball gone wrong. This sets up another puzzle. If electrons are always moving, how do they organize themselves? Think of electrons not as tiny dots, but as a buzzing swarm that follows strict patterns. Quantum mechanics forces them into orbitals regions where they're most likely to be found. These orbitals aren't neat little circles. Some are shaped like dumbbells, others like clover leaves. It's as if electrons are performing a cosmic dance routine, each with its own step pattern. And here's the rule. No two electrons in an atom can dance the exact same step in the exact same way. This is the Pauli exclusion principle. It's like a cosmic bouncer making sure no one wears the same outfit on the dance floor. This rule creates structure. It's why the periodic table exists. Elements differ because their electrons fill orbitals in specific ways, creating the rich diversity of matter we see around us. So let's get practical. What does this mean for everyday life? It means the colour of your t-shirt, the strength of steel, the sparkle of a diamond. All of it comes down to how electrons are arranged. Take colour, for instance. Atoms absorb and emit light at specific frequencies. That's why fireworks burst in different colours. Sodium atoms glow orange copper, shines green, strontium burns red. It's not random. It's the electron dance steps releasing energy in unique ways. And when millions of atoms get together in a material, the way their electrons collectively interact with light determines what colour you see. Snow looks white because ice crystals scatter all wavelengths equally. Water looks clear because its molecules let visible light pass through but block others. Your jeans look blue because the dye molecules absorb red and green light bouncing back blue. So the colours of our world aren't painted on the surface. They're born from atomic interactions with light. Here's a fun detour. Do atoms themselves have colour? Not exactly. A single atom is smaller than the wavelength of visible light, so it can't have a colour in the way we see it. What atoms do have are unique emission spectra, the light signatures they give off when excited. Astronomers use this trick to figure out what distant stars are made of just by analysing their light. In other words, every atom has a voice. Hydrogen hums in one frequency, helium in another, iron in yet another. Put them all together and the universe is basically a cosmic orchestra. And this leads us naturally to the next curiosity. If atoms explain the colours and textures of our world, how do they also explain the strength and stability of matter? Why does diamond cut glass while graphite made of the exact same carbon atoms crumbles under pressure? Why is steel stronger than aluminum but lighter metals can sometimes be more useful? The answers lie in how atoms bond, how their electrons are shared or transferred, and how those bonds shape the properties of the materials we use every day. That's where we're headed next. In the last chapter, we saw how atoms explain the solidity of objects, the colours of the world, and even the illusion of touch. But here's another puzzle. If everything is made of the same basic atoms, protons, neutrons, and electrons, then why does matter behave so differently? Why can carbon form a diamond tough enough to cut glass and also graphite soft enough to write with in a pencil? The answer begins with this question. How do atoms bond together to form materials with wildly different properties? Atoms rarely exist alone. They almost always connect, forming molecules and solids. The way they connect makes all the difference. Take carbon. Each carbon atom can form 4 bonds. In diamond, those bonds link in a perfect 3D lattice. Imagine an endless pyramid of pyramids, each carbon, holding 4 others in a rigid embrace. The result? One of the hardest substances in the universe. In graphite, carbon bonds form flat sheets stacked on top of each other with weak forces between layers. Like a pile of paper, the sheets slide easily, which is why your pencil leaves marks on paper. Same atoms, same element, totally different outcomes because of bonding. Which naturally brings us to the next curiosity: why do atoms even bother bonding? The short answer is energy. Atoms are always trying to reach lower energy states. By sharing or transferring electrons, they find stability. That's why sodium with one lonely outer electron loves to give it away, while chlorine, desperate for one more, snatches it up. The result is table salt so stable, you can sprinkle it on fries without fear of it exploding. Sometimes atoms share electrons equally, like 2 friends splitting a pizza down the middle. Other times, one atom hogs the pizza and leaves the other with crumbs. That's why some bonds are balanced covalent while others are lopsided ionic. Now let's make it practical. Why do these tiny bonding rules matter for the big everyday world? Because bonding determines properties. Metals like copper are shiny and conduct electricity because their electrons roam freely like a communal Wi-Fi everyone can connect to. Rubber stretches because its molecules are arranged like tangled spaghetti that can uncoil under pressure. Glass is brittle because its atoms form a rigid, irregular network with no room to bend. The magic of materials, hardness, flexibility, conductivity, transparency, all comes from how atoms decide to hold hands. But here's the kicker. Molecules aren't just building materials, they're life's toolkit. Water is the perfect example. Its bent shape and uneven charge distribution let it dissolve more substances than almost any other liquid. That's why it's called the universal solvent. Without water, life's chemistry wouldn't run. DNA, proteins, fats, all of them are molecules built from the same basic atoms, arranged in astonishingly complex patterns. Life is really just atoms playing Lego at the highest level. So the next time you eat a slice of pizza, remember the stretchy cheese, the crunchy crust, the tangy tomato sauce. It's all atoms arranged in different bonding patterns. Your dinner is a chemistry lesson you can taste. Let's add another twist. Atoms don't just bond, they sometimes fuse. Normally atomic nuclei are stable, glued by the strong nuclear force. But in stars under incredible pressure and heat, nuclei can merge. Hydrogen nuclei fuse into helium, releasing enormous amounts of energy. That's the process powering our sun and giving you daylight right now. fusion is the most powerful bonding of all, the one that turns simple atoms into heavier elements and floods the universe with light. Every atom of oxygen you breathe and every atom of calcium in your bones was forged in the heart of a star through fusion. So let's zoom out again. What does all this bonding and fusion mean for the universe as a whole? It means atoms aren't just tiny building blocks. They scale up to cosmic architecture. Clouds of hydrogen and helium collapsed into stars. Stars forged heavier elements. Supernovae blasted those elements across space. Planets formed. Life emerged. All because atoms interact in predictable, rule-bound ways. Without bonding, you'd have a universe of lonely hydrogen atoms floating in the dark. With bonding, you get galaxies, ecosystems, and humans making YouTube documentaries about atoms. But before we leave this part, let's play with one more wild idea: what happens when atoms push their limits. In neutron stars, the collapsed cores of massive stars, gravity crushes atoms so violently that electrons are forced into protons, creating neutrons. The result is matter so dense that a teaspoon of it would weigh billions of tons. In a sense, a neutron star is like one gigantic atomic nucleus, scaled up to cosmic proportions. It's a reminder that the rules of atoms don't just govern the small, they echo into the largest, strangest structures in the universe. And now the story gets even stranger. If atoms can scale up into stars and neutron-packed monsters, what does that say about the forces inside them? In part 6, we'll shrink back down to the subatomic scale, to quarks, gluons, and the strongest force in nature. Spoiler, it's the hidden engine behind nearly all the mass in the universe. So far we've seen how atoms behave in everyday life, how they bond, form materials, and power the stars. But here's a puzzle we haven't cracked yet. Inside the nucleus, protons should be repelling each other with incredible force. They're all positively charged. By the rules of electromagnetism, they should fly apart instantly, and yet they don't. So what holds them together? That brings us to one of nature's best-kept secrets, the strong nuclear force. This is the mightiest force in the universe, far stronger than electromagnetism and gravity. It's the glue that holds protons and neutrons together inside the nucleus. Without it, atoms wouldn't exist. But here's the twist: the strong force only works at incredibly short distances. Imagine duct tape that only sticks if the objects are almost touching. Pull the pieces apart even slightly and the tape stops working. That's how the strong force behaves, utterly dominant at tiny scales, non-existent at larger ones. So the natural question is, what actually carries this strong force? Enter gluons. If photons are the messengers of electromagnetism, gluons are the messengers of the strong force. They hold quarks, the smaller particles inside protons and neutrons, together. A proton, for example, is made of 2 up quarks, and 1 down quark bound so tightly by gluons that they can never escape. Try to pull a quark out and the energy you invest doesn't free it. It creates a brand new quark-antiquark pair instead. It's like trying to stretch a rubber band so far that instead of snapping it spawns another rubber band. That's why you never see quarks alone. They're always locked inside particles. Which leads to a fascinating detail: most of the mass of everyday matter doesn't come from protons or neutrons themselves. It comes from the strong force holding them together. Wait, what, isn't mass supposed to come from the Higgs field? Yes and no. The Higgs field gives particles like quarks and electrons their tiny intrinsic masses. But here's the kicker. Those quark masses only add up to a few % of a proton's total mass. The rest, around 99%, comes from the energy of the strong force itself. In other words, you, me, the Earth, and nearly everything you've ever seen are made of pure binding energy. Matter is really just energy tied in knots. Now here's another curiosity: why are protons stable while neutrons decay? A free neutron outside a nucleus will break down in about 15 minutes, turning into a proton, an electron, and a neutrino. But protons, as far as we can tell, they live forever. This tiny asymmetry is crucial. If neutrons were more stable than protons, the universe would look completely different. Hydrogen wouldn't exist, stars couldn't burn, and chemistry as we know it would collapse. The fact that protons won the stability game is why we have a universe full of hydrogen fuel for stars and water for life. But let's stir things up. Are protons really eternal? Physicists aren't so sure. Some grand unified theories predict that protons will eventually decay just on timescales, so absurdly long it makes your head spin. Estimates run to 10 to the 34 years or more. For context, the universe is only about 10 to 10 years old, so if protons do decay we won't be around to notice. Still, this possibility keeps scientists awake at night, because proton decay would rewrite our understanding of the cosmos. Entire galaxies, stars and planets would eventually dissolve into pure radiation. It's the ultimate nothing lasts forever scenario. And then there's the proton radius puzzle. How big is a proton really? For decades, experiments pegged the proton's radius at about 0.876 femtometers. But in 2010, a new method using muons, heavier cousins of electrons, measured it smaller, about 0.833 femtometers. That may sound like splitting hairs, but in physics that difference is massive. Why the discrepancy? Was the earlier measurement wrong? Or does it hint at new physics beyond what we know? After years of debate, later experiments leaned toward the smaller value, suggesting the mystery was due to measurement errors. Still, the fact that such a tiny particle can cause such big headaches shows how much we still don't understand. Step back for a moment. What's the picture so far? Protons should repel each other, but the strong nuclear force glues them together. Gluons are the carriers of that force, locking quarks inside protons and neutrons. Nearly all of your body's mass is binding energy, not particles themselves. Protons seem eternal, but may not be. They could decay over timescales beyond imagination. Even measuring a proton's size is tricky, hinting at mysteries still unsolved. So where does this leave us at the edge of extremes? Push atomic rules hard enough and you get neutron stars, giant atomic nuclei held together not by chemistry, but by gravity, and the strong force working over time. Studying them might unlock secrets we can't reach in labs on Earth. And if we look further still, we stumble into wild ideas, string theory, multiverse models, speculations that our entire universe might itself be like an atom inside a grander reality. Whether that's true or not, one thing is clear: atoms aren't just building blocks. They're keys to the deepest architecture of the cosmos. The lasting thought from part 6. The strong force isn't just the glue inside nuclei, it's the hidden engine of mass itself. The silent architect of reality, shaping everything from the smallest proton to the largest galaxy, without ever letting us see it directly. We've travelled from the first fractions of a second after the Big Bang all the way to the powerful forces inside protons. But now let's turn the telescope inward, because the atoms that make you are on a journey too, and their story doesn't end when yours does. So here's the question: what happens to your atoms after you die? It sounds grim, but really it's a story of recycling on the grandest scale. The law of conservation of matter says atoms can't be created or destroyed. They only change partners, reshuffling into new forms. That means the atoms in your body, about 7 octillion of them, are ancient travellers. Long before they were part of your skin, your bones, or your breakfast, they were forged in stars, drifted across space, and cycled through countless other forms of life. And long after you're gone, they'll keep moving. Let's start with something simple: the water in your body. You're about 60% water, which means most of your atoms are part of H2O molecules. When you die, that water evaporates or seeps into the ground. Some becomes vapour in the air, joins clouds and falls back as rain. Some feeds plants, which then get eaten by animals or by someone's great-grandchild. So the glass of water you drink today may contain molecules that once flowed through the veins of a dinosaur or swirled in Cleopatra's bath. Time doesn't erase atoms, it just passes them along. Now let's move on. What about the carbon in your body? Carbon makes up about 18% of you. It's in your DNA, proteins, fats, all the stuff that keeps you alive. When your body decomposes, bacteria break those molecules apart, releasing carbon dioxide back into the air. Plants absorb it during photosynthesis, turning it into sugars. Those sugars get eaten, and suddenly your carbon atoms are part of a bird, a tree, or someone else's body. So in a very real sense, you don't disappear. You just spread out, becoming part of the world around you. But here's a quirky detail: not all your atoms stay close to home. Some elements like nitrogen leak into the soil and fertilise plants. Others drift into rivers and oceans, circulating around the globe. and a few like helium atoms produced in your body through radioactive decay are so light they escape Earth's gravity entirely. That means bits of you will eventually float off into space, joining the interstellar wind. Talk about leaving a legacy. Now here's a fascinating twist: cremation accelerates this recycling. When a body is cremated, the intense heat breaks molecules apart almost instantly. Hydrogen, carbon, nitrogen, oxygen. They all turn into gases that rise into the atmosphere. A small amount of ash remains mostly calcium and phosphorus from your bones. Those atoms may end up in soil nourishing plants. The gases, meanwhile, mix with the atmosphere and circulate around the planet. So the atoms from a cremated body might become part of a tree in Brazil, a raindrop in India, or the breath of a child in Alaska. But let's zoom out even further. Do atoms last forever? That depends on which atoms we're talking about. Many, like carbon, oxygen and hydrogen, are stable and may survive until the heat death of the universe. Others, like radioactive isotopes, eventually decay into different elements. And then there's the proton. We talked about this in part 6, it seems stable, but some theories say it may decay in the distant future. If that happens, even the atoms in your body won't last forever. They'll eventually dissolve into pure radiation. But don't worry, we're talking about timescales so vast they make the age of the universe look like a coffee break. So let's flip the question. How old are the atoms inside you right now? The hydrogen in your body is over 13 billion years old, formed just after the Big Bang. The carbon, oxygen and iron were forged in stars billions of years ago, then scattered across space by supernova explosions. The calcium in your bones was once part of the heart of a dying star. Every atom in you has been on a journey longer and stranger than any human history. You're literally made of stardust, and when your atoms leave you, they'll continue their cosmic road trip. Here's the truly mind-bending part: your atoms may one day be part of something unimaginable. A carbon atom in your body could end up in the DNA of a future species on another planet. A calcium atom in your teeth could become part of the rocks on Mars. A hydrogen atom in your blood could fuse inside a star trillions of years from now, releasing light into some distant galaxy. Your story ends, but your atom's story never does. And here's the deeper reflection: atoms connect us all. The breath you just took likely contains oxygen atoms exhaled by someone thousands of years ago. The iron in your blood might once have been part of a supernova. The calcium in your bones could someday become part of a mountain or a seashell. We live short lives, but the atoms that make us are nearly eternal. They tie us to the past, flow through the present, and will carry on into the future long after we're gone. As we close this journey, one final image remains. In the grand dance of the universe, you're both temporary and timeless. Your consciousness, your experiences, your story, those are fleeting. But your atoms are ancient travelers. They've been part of stars, oceans, trees, animals, and now you. And when you're gone, they'll move on again quietly, weaving you into the fabric of the cosmos. In the end, nothing is ever truly lost. The atoms that form you today will one day shine in new stars, ripple through new oceans, or breathe life into new beings. And that's a legacy bigger than any of us could ever imagine.